Today's webinar, as you all know, I assume, is on nitrate removal from potable water. My name is David Chesnick. I'm the Director of Marketing for ResinTech. With me again is Kaitlyn Clark, our Ion Exchange Technologist, Peter Myers, our Technical Director, and Frank Da Silva, our Western Region Sales Manager. Again, for those of you who don't know ResinTech, and I'm assuming most of you do, but just in case, we just moved into this fantastic new facility in Camden, New Jersey. All of our products are made in this building. And we just had a tour a week ago from some of the Culligan folks who just were blown away by what they saw. So hopefully all of you will get a chance to visit our new facility at some point in the future. And we'll be operating on all cylinders, and you guys will be blown away as well. But just in case you don't know some of the products and services that we offer, really, we brought together all of the divisions of our company, Aries Filterworks, ACM Technologies, and ResinTech, to offer you various bulk media offerings in terms of resins and carbons and specialty media, as well as made in the US filter cartridges, high purity lab water systems, water recycling systems. And then we have a full service high-end lab here as well that Kaitlyn's going to be talking about a little bit in her presentation. And then, of course, a lot of other services as well, like resin regeneration, technical consulting, even private labeling, and so on. So if you were unaware of some of those services, reach out to your ResinTech technical representative, and they'll be happy to help you get oriented around them. So today's presentation is going to be about nitrates. Here are the rules of the road. Kindly mute your phones for the presentation. We're not going to use the hand raising function. Instead, we're going to use the Q&A function. We'll curate them, and then at the end, Kaitlyn will address them. And of course, we're going to make this presentation available via YouTube and our website. You can always ask your rep as well. Today, actually, we're streaming on Facebook Live on our Facebook page if you have any interest. So today's presentation is going to be on nitrates. Kaitlyn Clark has been with our company for about 6 years, and she's had the good fortune of working under the tutelage of two of the giants in ion exchange, really. Peter Myers, our technical director, who brought us through bulk contaminants and trace contaminants over the course of the last month, and Michael Gottlieb, our founder, the founder of ResinTech. So with those two people as her teacher, I think we're in for a good presentation. So I'm going to turn it over to Kaitlyn.
Hi, everyone. Today I'm going to be talking about nitrate removal from potable water. So like Dave said, I've been with ResinTech since 2013. I started out in college working in the lab on an internship. I didn't know much about ion exchange at the time, but I quickly became fascinated with it. Now you fast forward now 8 years later, I no longer work in the laboratory, but I specialize in applications support and technical support for all you guys. So today, the webinar is going to be a bit of an intermediate level discussion. I'll go through a brief overview of nitrate as a contaminant, how it's regulated, and some general chemistry to get us started, as well as a few other treatment methods used for reducing nitrate in water. Then we'll take a deeper dive into nitrate reduction by anion exchange and then do questions. So how does nitrate get into water in the first place? Most nitrate is entering water through agricultural sites, fertilizer, and livestock. Mutastic number ones are the main culprit for nitrate entering potable water. In residential areas, lawn fertilizer waste, septic tanks, and domestic animals also contribute to nitrate in the groundwater. So why do we not want to have nitrate in the water? So there's some primary health risks. It and nitrite bind to hemoglobin in your blood and reduce oxygen saturation. This is usually referred to as blue baby syndrome. It mostly affects very young infants and fetuses, not so much adults because we're larger, obviously. And there's a secondary health risk that is becoming more of an issue in recent years. Nitrate's an excellent nutrient source, which is why we use it for fertilizer, but it also is a good source of nutrients for algae, and some nitrate runoff areas are susceptible to becoming home to harmful algae blooms, which we do not want. So nitrate as an ion it forms freely soluble salts. It's symmetrical, so it doesn't really break apart into NO2 or NO. It typically stays NO3. It's monovalent like chloride, and uranium is often a co-contaminant with nitrate and potable systems. Luckily, an ion exchange resin used to remove nitrate will also remove uranium. The maximum contaminant limit set by the EPA for nitrate in potable water is 10 ppm or 10 milligrams per liter as nitrogen. Labs that test for nitrate will usually report nitrate as nitrogen, but they might also report it as calcium carbonate or as nitrate. So aside from anion exchange, a few other methods used for nitrate reduction include biodenitrification with bioreaction, membrane processes such as RO, and of course, ion exchange. Each method has its advantages and disadvantages. Today, we'll be focusing on the anion exchange resin. So without further ado, let's dive into the beef of nitrate removal by anion exchange. We'll do a quick ion exchange theory recap, and then talk about choosing nitrate resin, sizing a system, and creating a regeneration strategy. We'll finish up by talking about resin life and touch on some issues that can arise with nitrate removal systems and how to combat those. So if you attended our first two webinars on trace and bulk contaminants, you'll likely remember that ion exchange resins are plastic beads that take salt out of water and put other salts back in. The put other salts back in part is an important thing to note. Since anion exchange resins used for nitrate removal are operated in the chloride form, the effluent water will be enriched with chloride and may, in some cases, exceed the 250 ppm secondary MCl for chloride. So here's a simplified equation for what's going on in a nitrate removal system. The nitrate in the water contacts the resin in the chloride form. The nitrate basically shoves the chloride off of the resin and into the water. And when the resin's exhausted, it's time to regenerate by putting a whole bunch of chloride brine into the resin to shove that nitrate back off. Simple enough, right? Yeah, but we have all the other ions in the water to be aware of. For performance estimates, we need to know the whole water quality or as much as possible to give good recommendations. Don't have a water analysis? No problem. We can either make estimates from what we have, or we offer testing services for your water that we can use to help you decide on a treatment scheme. The anions that we really need to talk about are sulfate, alkalinity, chloride, and of course nitrate to calculate a throughput. We also like to know hardness to assess scaling potential in the system. TDS and conductivity help us understand the balance. And if we know total suspended solids, we can make recommendations to help you guys avoid physical contamination in the bed. pH also helps us determine how much of an effect the pH will have during service cycle, since the anion resin will also remove the alkalinity for a brief portion of the cycle. No need to panic though, we'll hit all those nails as we carry on. So this is our water testing kit. If you'd like more information, go ahead and shoot us an email. So let's dive right into the types of anion exchange resins used in nitrate reduction applications. We have the resin that's got dimethylethylenolymine functionality. This is a standard type 2 anion resin, such as the SPG2HP. Type 1 is also capable of removing nitrate, but it has a greater tendency to impart a fishy odor on the water, so we tend to avoid that in potable applications. Next, we have the nitrate selective resin. This is a triethylamine. For us, that would be SIR 100HP. And finally, we have the super selective resin. It's the tributylamine we call it SIR 110. It also is used for perchlorate and PFAS removal. So each of these resins has advantages and disadvantages, and our choice in resin really depends on what else is in the water. So if you notice the K values, that's the selectivity for nitrate against chloride, doesn't really change a whole lot for each of the resins. You go from 3 to 25, which is really a huge jump. The big thing to note is that the sulfate selectivity gets really small when we get to the super selective resin. As an aside, K tells us how many pounds, grains, ppm, whatever, of nitrate the resin can remove for every pound, grain, or ppm of chloride. So for the SPG2, 3 nitrates will be removed and put onto the resin for every chloride that comes back off in the service cycle. And the opposite is true during the regen cycle. 3 chlorides from the brine will push 1 nitrate back off the resin into waste. So let's talk about nitrate removal versus softening, because a lot of times we call a nitrate unit an anion softener. So I'm just going to briefly touch on the differences. So they're both operated in the salt form, where the anion is using the chloride from the brine, and the cation, the hardness softener, is using the sodium from the brine. The K for the nitrate against the chloride is the same no matter what the TDS is, whereas the K for hardness against sodium is higher when the TDS is low, somewhere under about 1,000 ppm, which you see during the service cycle. And it gets lower at real high concentrations in excess of tens of thousands of ppm, which is what we see during the regeneration cycle. Since nitrate doesn't change selectivity, more pounds of salt are typically needed to keep leakage down in the service cycle. You might see 15, 20, or even more pounds of salt required to get under that 10 ppm MCL. For most softening applications, 10 pounds is plenty. Since concentration doesn't change the nitrate selectivity, we don't need really concentrated salt for regeneration like we do with hardness. 5% salt is plenty for the anion, and in fact, lower is usually better to reduce scaling and prevent the anion resin from floating. It floats above about 12% salt, and that causes issues with the regeneration. The cation, on the other hand, needs the 10% salt at least. So as a result, while the 2 units may look pretty similar, they have a couple differences. The anion salt ejector has to be smaller to give a lower concentration, and you're going to want to cut the backwash flow rate in about half because the resin is less dense, so it'll expand a lot more during your backwash, and we definitely don't want to lose any resin from the vessel if we can help it. So how do we choose the right resin? We ask ourselves things like, well, how high is the TDS? How high is sulfate? Are there other contaminants in the water that need to go? SPG2 has a higher maximum or total capacity than the SIR 100 or 110. So at higher TDS, if the sulfate is lower, say like 10 ppm, then the SPG2 is a great choice. Higher capacity means longer service cycle, and the resin itself is less expensive to boot. SPG2 is also good at removing arsenic, chromate, and uranium. So if those guys are present in the water too, then SPG2 can kill 2 or more birds with 1 stone. But what about if the sulfate is higher, say 50 or even 500 ppm? At that point, you'd probably want to consider using either the SIR 100 or the 110. Since sulfate is also divalent like the hardness ions, it becomes more selective as TDS goes down, making it a major competitor against nitrate, especially with the type 2 resin. Having a lot of sulfate present also increases the risk of nitrate dumping off of the resin, which is when leakage would be higher going out than it is coming in. This dumping effect only occurs if the system is overrun, i.e. the timer broke, or maybe there wasn't enough salt in the tank for the regeneration. So for systems that are not frequently monitored or have high sulfate, the SIR 100 or the 110 are likely the best choice. SIR 100 is a good middle of the road kind of resin. It's a little more expensive than the SBG2, but it's less expensive than the SIR 110. It will almost never dump unless the water has unusually high sulfate, which is typically outside of the potable range, and typically has service throughputs that are pretty comparable to the SBG2. SIR 110 can be a good choice if sulfate is really high or in waters that have perchlorate or PFAS, another bird and stone situation. So now that we've picked a resin, we need to size the tanks. For municipal systems and residential systems alike, flow rate is the key to sizing. The target linear flow rate for each is 10 GPM per square foot. All this really means is the flow rate on the cross-sectional area. The service flow rate is going to be 2 to 4 GPM per cubic foot, and this relates to the optimal flow rate for the resin itself and not so much the equipment. So bed depth is also important. Deeper is usually better. So for larger systems, we want to aim for about 5 feet deep bed zones. This maximizes our working zone and minimizes the impact of unused resin below the tank distributors. Since residential systems are smaller, we can't fit a 5-foot deep bed in a small fiberglass tank. That's okay though, because fiberglass tanks won't have as much resin below the distributor, and flow is more intermittent. So it's not going to be as big of an effect as it would be on these larger systems to have a slightly smaller bed depth. So here's some examples of residential systems. On the left, we have a point of entry system. It looks a lot like a regular water softener. It has a timer or gallonage setting on top that you can use to set the regeneration. We can help you with that. It's not going to be the same as sizing or regenerating a cation resin. So shoot us an email and we can absolutely help you size and get some throughputs for those kinds of systems. On the right, we have a point of use system. They generally don't get regenerated and they're usually under your sink. Instead, you would just be replacing the cartridges periodically. So up next, this is what a municipal system will probably look like. This monster has probably at least 200 feet of resin in each vessel. They can process thousands of gallons per minute and provide water to entire neighborhoods, towns, or even cities. A system like this can process millions of gallons a day. So this is another municipal system, and I just wanted to call it out because it's a packed bed, which is countercurrently regenerated, and it has the super selective SIR 110. Systems like these can obtain exceptionally low nitrate leakage, especially in waters with really high TDS and sulfate, like the one in the picture in Arizona. So here are some minimums and maximums for design guidelines. These are consistent for most salt form ion exchange systems. You typically don't want the runtime service cycle to be less than about 4 hours. For one thing, regenerating the resin too frequently will shorten resin life because the resin gets tired, essentially. For another thing, keeping a regeneration on schedule every 4 hours or less becomes an operations challenge. Minimum service flow rate is going to be 0.5 GPM per cubic foot. If it runs too slowly, there's a risk of channeling. Same thing applies for the minimum linear flow rate. Channeling just means the water either trickles down the side of the vessel or through a smaller portion of the bed. And when this happens, not all the resin can do its job. If it doesn't see the water, it can't remove the nitrate. Maximum service flow rate should be below 5 GPM per cubic foot on a continuous basis. 10 GPM is okay as an intermittent peak flow rate. If the service flow rate is too fast, the water and resin don't have contact between each other long enough for nitrate to be picked up efficiently. And then the maximum linear flow rate is 20 GPM per square foot. And this is to avoid having excessive pressure drop, which would lead to bed plugging or equipment and resin damage from excessive pressure. So how long will the resin last? The average resin can make it through 3,000 service regen cycles before it wears out. So a resin that regenerates once a day would theoretically last about 8 years, and one that regenerated, say, 4 times a day would only last 2. There are other factors aside from cycling that affect resin life, but typically 5 to 7 years is a good baseline estimate for life. Some other factors that affect life, all resins are going to lose capacity over time. Physical resin loss occurs at about 1% per year. This is a case where the resin is literally lost from the tank, usually during a backwash. Chemical losses account for about 2 to 5% capacity loss per year for chloride form resin. Resin fouling increases apparent capacity loss also. And types of fouling for anion resin are usually going to be like an organic issue or iron or manganese. Once the resin has lost over 25% of its capacity, it's usually time to replace. Periodic wellness checks can help keep a system running smoothly and catch problems before they become problems. We offer routine testing on resin in our lab. So here are some less natural, or at least external factors that affect resin life. Chlorine in the feed water can oxidize the resin, which will eventually turn it from a plastic bead into like a plastic mush. And the chlorine and oxidants also create disinfection byproducts, and those we don't like to see in our water. Frequent regeneration tires the resin out more quickly, and foulants such as organics, iron, and manganese get stuck inside the bed, which prevent the nitrate from finding the bead in the first place. Water that's biologically active, aka it has the wrong kind of bacteria, can also foul the bed and block nitrate from seeing the bead. If you think your bed might have any of these problems, let us know and we can help you diagnose and treat for these. So here's our lab. It's brand new here in Camden. If you see the young lady over there testing the resin in the graduated cylinder, I'm pretty sure that's a customer sample. If it happens to be ResinTech resin, standard testing for resin is complimentary. So now, once we have the water analysis and we have a basic idea of what might work, low sulfate would be SPG2, high sulfate would be 100 or 110. There are lots of other ions in the game. We want to get the job done right, so what should we do? If you send us your water analysis, we can run performance projections with our Mistec software to guide you towards the right choice. These only take a few minutes on the computer, whereas a pilot study could take days or even weeks. I'll now go through some examples of nitrate projections. We keep chloride, alkalinity, and nitrate constant in these and vary sulfate to illustrate the difference in resin performance at different sulfate levels. So here we have sulfate at 10 ppm. This is our low sulfate. As you can see, the SPG2 beats both the SIR 100 and SIR 110 in throughput capacity. And just for reference, bed volumes are equal to 7.5 gallon per cubic foot. In this example, the resin's total capacity is driving the throughput primarily. So when we increase our sulfate a little bit to 50 ppm, the SPG2 falls behind a little, and the nitrate selective and super selective resin have more throughput. But what happens when we really increase the sulfate? So at 500 ppm of sulfate, the SPG2 falls very far down the line on the throughput, and the SIR 110 comes pretty far ahead. And not only did the SPG2 fall pretty far behind, if we run the system past the breakthrough point, we get a dump on the SPG2. The SIR 100 and 110 don't dump. The reason for the dump is the high sulfate, and it can be a little bit higher or even more higher than the influent nitrate concentration. So now I'm going to talk a little bit about regeneration. We have co-flow and counterflow. Co-flow would mean service and regeneration are going in the same direction. Usually this will be downflow. It's the best known and most forgiving way to regenerate. Countercurrent is more complicated, but gives higher salt efficiency and lower leakage. I could spend over an hour talking about regeneration alone, but for today, we'll just compare the two and go over the more basic countercurrent regeneration design. So here we are at 5 pounds per cubic foot of salt. The co-flow unit is hovering around the 10 ppm MCL, whereas the countercurrent unit can get much lower into like the 4 or so average leakage range. When we increase the salt dosage to 15, they both achieve reasonably low leakage, though the countercurrent is still lower. But the main thing is it takes 3 times more salt for the co-flow unit to produce this more reasonable leakage. So here's what a basic picture of a co-flow vessel might look like. The water comes in through the top and goes down through the bottom, and so does the regeneration chemical. This system can be backwashed to clean the resin inside its own tank because it's designed to have 50 to 100% freeboard. The good brine hits the top of the bed first and makes its way down. As a result, more nitrate is left at the bottom of the bed, which leads to the higher leakage. So the highlights here, it's the simplest, most inexpensive, and most well-used form of regeneration. The main drawbacks are that it's a little bit less efficient and you have higher leakage, especially at high TDS. So the other option would be a countercurrent system. I'm going to talk mostly about the packed bed, since it's the most simple of all the countercurrent regeneration strategies. So in this system, the influent water comes in through the top and goes out the bottom, and the regeneration chemical is fed through the bottom and goes up through the unit. Freeboard must be limited to keep the bed packed. Fluidization for the resin is not good. It makes regeneration less effective. So backwash and cleaning must be done in a separate vessel for this kind of system. Since the good brine hits the bottom of the bed first and makes its way up, less nitrate is left at the bottom of the bed, so less is there to leak out during the next service cycle. So the pros and cons for countercurrent regeneration. It has very high salt efficiency and can give the lowest leakage possible. especially in waters with high nitrate. They're more complex and more expensive than a co-flow unit, and they require external backwash to clean debris from the bed, which we have to do because we don't want the bed to plug up. And more can go wrong if the bed fluidizes, regeneration doesn't work very well, and water quality drops. So how do we develop a regeneration schedule for these kinds of systems? Each part of the regeneration is important. We start off with a backwash. This cleans the physical debris from the bed and unpacks the bed to allow void spaces for the chemical to get in and do its job. Typically, we take about 15 minutes for the backwash. Then we inject our brine chemical. This needs to take long enough so the resin has enough time to react with the chloride and push the nitrate off. The displacement rinse is usually done at the same flow rate as the chemical injection dilution water. This flow rate is twofold because some of the brine is still in the bed at the start of the dilution, the slow rinse, which allows more brine to hit all of the resin as you slowly make your way through the rinse. It's also helping to avoid osmotic shock or damage to the resin because rapid changes in concentration can cause damage because the resin will change its shape a little bit when chemicals are going through. So the slow rinse helps minimize this by changing the water concentration more slowly. The fast rinse is usually done at the service flow rate and flushes any chemical left in the bed out and gets the resin ready to return to service. When all is said and done, the whole regeneration is typically going to take an hour to an hour and a half. So is softening necessary for nitrate removal systems? During the service cycle, it's not as necessary. The typical rule of thumb, you want to be about 10 grain per gallon hardness before you think about necessarily needing to soften, or if you have to soften for another reason, then you would likely want to soften. The more key thing is going to be during the regeneration. You're more often going to want to regenerate the dilution water to try to avoid calcium sulfate scaling in the bed. There's some other ways to minimize scaling during the brine step. You can get soft salt, but this is expensive and sometimes hard to find. You can soften the dilution water, as mentioned before, to reduce the hardness contribution from the feed. If you reduce the brine concentration itself and start at the start of regeneration using 2 to 3% instead of a 5%, this can help to keep the hardness and the salt down and prevent scaling. You could also increase the flow rate of the injection to push the salt through the bed faster so scale doesn't even have a chance to form. You could also use the SR 100 or 110 instead of the SPG2 because they're less susceptible to brine scaling because they don't pick up as much sulfate. So we hear a lot of times the pH effect with the anion exchange resin. Since anion exchange resins remove anions, they also will remove alkalinity because it's also anionic. As a result, the resin will remove the alkalinity at the start of the cycle, and as a result, the pH drops and the water corrosivity goes up. Since alkalinity is one of the least strongly held anions, the pH effect is temporary. So the pH will drop and then the alkalinity breaks through and then the pH goes back up to normal, typically within the first couple hundred gallons in the service cycle. We can estimate how much the pH will drop and for how long using our projection software. All we need is starting pH and the alkalinity. So then Resins foul over time with different contaminants. We can have like a plastic bag where the bead gets coated and ions can't get in or out. This happens with organics or iron. Usually this type of iron fouling on an anion unit is with iron bacteria or organic iron. We can have a sponge effect where something fills up the spaces among the beads and prevents equal flow. This would be something like dirt and physical debris and can often be backwashed out. Or we get some super ions, typically iron cleaning chemicals that have really high selectivity for the anion resin. So they get in, but then they don't get out. Things like citric acid, some of the phosphoric acid based iron cleaners can do this to the anion resin. So while they're really good for regular hardness softening resin, you don't typically want to use these kinds of iron cleaners on the anion to avoid this issue. So this is concluding the presentee part of the webinar. The key ideas I want you guys to take away with you today are water analysis is key to designing the system. The more we know, the better off we are. Sulfate is king in nitrate removal. High sulfate, you need a higher selectivity resin like the SIR 100. Low sulfate, you want to use something like an SPG2. And regular wellness checks on the resin can help you keep your system running smoothly and find problems before they become problems. So without further ado, I'll open up the floor for questions.
Thanks, Kaitlyn. Okay, I got a couple of questions for you.
Okay.
Here's a question from the chat. What do you recommend as resin cleaners?
For anion exchange, typically it's easier to take a lot of the foulants off with slightly alkaline water. So adding a little bit of alkalinity with some caustic is a good way to remove like organic foulants.
Okay, another question via the Q&A. Chad Hauser wants to know, does nitrate affect livestock?
Used anion and used nitrate resin.
Hold on a sec, Peter. So Dave just asked me if it affects livestock. So I'm going to answer that one first, and then I'll have you ask me again the other one. Yes, it could affect livestock in the same way, but since livestock, cows and such are such large animals, it would take quite a lot of nitrate to hurt the livestock.
Yeah, they're a whole lot less susceptible to nitrate in the water, and there's nitrate in a lot of the grains and the grasses that they eat.
Okay, you can ask your question again.
What kinds of tests do you do on spent nitrate resin?
We test the total capacity and the salt splitting capacity, and we take photos to see if there's any foulants on it, and we can perform TOC testing for the organics if we see visual evidence, which can be seen during the pre-treatment steps.
Do kinetics affect SPG2 differently than SIR 100 or SIR 110?
Yeah, so the SPG2 is a little bit better kinetically than the SIR 100 or 110, but for typical systems in nitrate removal, as long as you're within that 2 to 4-ish GPM per cubic foot range, they're all pretty equal for nitrate. The kinetics kind of enter in more so with some of the really big bulky ions like the PFAS and perchlorates.
Kaitlyn, I have a couple others.
How come you can't stir the resin and the brine up and get just as good of results?
Why can't you just stir the resin and the brine up for the regeneration and get equal results, because that would be more of a stirred equilibrium. So eventually the brine and the nitrate and chloride in the brine and the nitrate and chloride in the resin will come to an equilibrium. If you're moving the regenerate through and it leaves the resin, it's taking the nitrate out and you keep a concentration gradient. Think Le Chatelier.
What makes a nitrate selective resin deselective for sulfate?
The nitrate selective resins are deselective for sulfate due to their functionality. They kind of have a more bulky matrix. So since sulfate's divalent, it needs two sites right next to each other to bind to the resin. So since these guys are bulkier, it's a lot harder for them to find two sites next to each other to get in for the sulfate.
Do we have any data about the selectivity for thiosulfate? And would you think it would be a super ion or not?
That I'm not sure about.
Okay. Fair enough.
Do you have any idea on that, Peter?
Is there any bead size difference between a nitrate resin and other types of resin?
There can be if it's screened, but you're gonna have the same bead size for a typical Gaussian resin, no matter what. The actual size is not really different. It's at a microscopic level that their difference in size kind of comes in. Dave asked if you knew anything about the thiosulfate, Peter.
As what?
Do you know anything about the thiosulfate?
I don't have a selectivity value at the tip of my fingers, but I doubt it would be much different than I don't think it would be a super ion. I think it would be similar to most other ions.
Okay.
Mhm.
Can you use potassium chloride for regeneration? Yes, you can absolutely use potassium chloride. It's the chloride is the key for the regenerant chemical, and oftentimes potassium is more preferable because it's better for the soil than the sodium is. You might just have to finagle the concentrations.
Does ResinTech recommend a support bed in a nitrate removal system? Would you put Babble down at the bottom of the tank?
Yes. Yeah, you would have gravel at the bottom of the tank to keep as much resin above the distributor as possible. Since it's less dense than the cation resin even, then you're still all right with the backwash. How does the capacity change using potassium? The capacity doesn't change appreciably using potassium. You just might be using a slightly different number of pounds because of the difference in molecular weights.
Use anything besides potassium chloride and sodium chloride?
Theoretically, you could use anything chloride. Ammonium chloride is possible, although it gets a little more complicated. But most of the time you're using the sodium chloride or the potassium chloride.
What's a minimum temperature you can operate a nitrate system at?
You don't want to get too much below about 40 degrees Fahrenheit. As you get closer to freezing, ion exchange in general starts to not work as well. And if you get the freezing, it really doesn't work well at all.
So what happens when a resin wears out?
Well, the plastic gets kind of spent to a point. It might not necessarily look worn out, but over time, the plastic just kind of starts to get tired and it'll deteriorate over time.
Does it break down physically?
Sometimes it does and sometimes it doesn't. A lot of times it'll break down physically to some extent, but sometimes it doesn't break down very much before you see it start to wear out.
Would life be longer in a co-flow unit or in a packed bed?
In theory, they could be equal, but with the packed flow bed, you have a greater tendency to possibly break down the resin as it's hitting the top of the bed during regeneration. It's a little bit harder on the resin than a co-flow bed would be physically.
Kaitlyn, I have a couple others,
Any other questions?
unless
I
Peter's,
don't see any others.
Dave's got some.
Dave has some, good.
okay. There were a couple of questions that were sent to me directly. So what are the inlet water quality parameters that people need to be aware of? In particular, you know, hardness, iron, manganese, and suspended solids.
Yeah, so for the hardness, if you're above around 10 GPG, grains per gallon hardness, that's when you would like to think about using a softener. For iron and manganese, you don't want to be above about half a ppm of iron or a quarter of a ppm of manganese. And for suspended solids, you don't want to be above 1 ppm. Any suspended solids will get stuck in the resin bed over time.
Yeah, all those values are too high, you're gonna foul.
For residential, if the residence has an existing softener, should a nitrate unit be installed before or after the softener? And can you top off a softener with nitrate resin?
If possible, you want the nitrate removal to be after the softener. And whenever possible, you generally don't want to top it off with nitrate resin. You don't want the softener and the nitrate resin to be in the same vessel because it leads to a much greater chance of scaling during the regeneration because there's a lot of sulfate and alkalinity present on the anion.
It will scale.
Yeah, but it is done sometimes and works, but there will be some scaling.
And I think there's one more answer in the chat. I'll let you read that.
Okay, so yeah, I have a customer that uses 2 SPG2 20x2 filters, and after about 2 inches of the bed is used, he has breakthrough of phosphate. Should he be using a different anion for phosphate removal?
These are cartridges.
He probably has to change pH.
Okay, yeah, so it might be a pH issue more so than the resin itself.
Whoever that is, if you want to reach out to us directly at info@resintech.com or webinars@resintech.com, give your contact information. We'll track down an answer for you.
And that's if you could just use soft water for regen when it's over 10 grades.
Mhm.
Scaling is unlikely in the service cycle.
Okay, and I think there's one more question in the chat panel. When hardness is greater than 10 grains per gallon, can we just use soft water for regen?
Yes, you can use soft water for regen. It's not often, it's not going to scale as often in the exhaustion cycle. The more important thing is during the regeneration cycle.
Okay. Thanks, Kaitlyn. Oh, there's one more. Is it possible to get CE credits? We're actually looking into that. So Linwood, I'll let you know if CE credits are available with the WQA. We've had some conversations about that. Okay. Kaitlyn, what's the next slide? If you don't mind putting up the next slide for the QR code. If everybody has their phone, you can scan that. Give us your feedback on today's webinar. Tell us how to improve these going forward and make them as useful as possible to you and kind of hone our content. I'll give you a couple seconds to just scan that. And then I will let you know that our next webinar will be on softening, Wednesday, April 28th, same time, 11 Eastern. Frank De Silva is going to present this one. I know a lot of you know Frank, so we're looking forward to that. And we will once again be sending out an email so you can register for that independently. Today's webinar was recorded. It will be available on our YouTube channel later this week. And you can always reach out to your ResinTech, ACM, or Aries technical representatives. If you have any questions about today's content, or you want to get a copy of today's presentation, we're happy to get that to you. Kaitlyn, thanks so much. I know you worked really hard on today's presentation. Here's Kaitlyn's contact information. She's missing an I in her own name. That could be my fault, though.
I don't think I wrote my name here.
But nevertheless, feel free to reach out to Kaitlyn if you have any questions. And we appreciate everybody joining us today. So we'll see you on the 28th to talk about softening with Frank. Thanks so much.
Yep. Thanks, everybody.